So we have chapter 1.4. This is 1.4 of precalc. Today we're going to talk about a lot of different things here. It's not necessarily ground shaking. Takes up a little bit of space, takes a little bit of time to do it, but there's not a lot of work to it. That's the beauty of this. If you have a graphing calculator, it makes it a little bit easier towards the end of this lesson. But all the rest of it is all about trying to make sense of a graph that's in front of you or of an equation. So the first thing, I want you to be able to describe, if I told you from -3 to 5, what is the graph doing? I want you to be able to look at the graph, potentially plug some values in, and say, the graph is increasing. It is decreasing, or is it staying constant? And so we have definitions on the left-hand side there, more wordy type things. And then we have the diagrams. I think if I look at the diagram, I could point a few things out. What it says that if I start at x1 and move to x2, so you're always moving to the right. When we move to the right on the numbers, it gets larger, yes? So what it's saying, that if I take a value x1 and plug it into the function, I get f of x1. If I plug in x2, I get f of x2. If the value moving to the right of those points gets larger, as in it increases, the function is increasing. So if the value of the numbers going in gets larger and the outputs get larger, the function is said to be increasing. On the flip side, if I put in a larger x value and the value on the out is lower than the out of the first point, that function is considered to be decreasing. And on the bottom here, from x1 to x2, you can see that there's no change. That would be considered constant. So all I'm going to ask you to do for this first group is to look at a graph and tell me the interval where it's increasing, decreasing, or constant. There is not anything that says that they have to have all three. They may have only one or two, or have all three parts. There's options. So again, you can look at the more wordy side of things. Basically it says if x1 is less than x2, then their values of x1, f of x1, has to be less than f of x2. It's increasing. The same thing here, but if the first point is bigger than the second point, then it's decreasing. And if they're the same, it's constant. That's what the words say. So let's put this to practice. So, use the graph of each function to estimate the intervals to the nearest 0.5 units on which the function is increasing, decreasing, or constant. And then we'll support this numerically. So look at the first one. The first one is a what? It's a parabola. It's a quadratic. Is there parts of this graph that's decreasing?
No.
Yes. I think we can see that if I start on the left, I will fall to the vertex. And then at the vertex, I will go back up, and I'll be increasing. Is there any constant part to this? And the answer is no. So at some change right there, right? It switches from decreasing to increasing. So let's list that. Decrease. So if I wanted a decreasing interval, how would I list that? Using interval notation. I think that might be the fastest, easiest way. What's the smallest number that it starts to decrease? Where is the graph starting to fall?
Oh, right at, what is that line?
-3, because -3 is the last number on my graph, but that arrow says it goes on for. So technically, it will keep going. Is there any x value that I'm not allowed to put into a quadratic? No. So could I choose a -1 million? And if I chose a -1 million, I think that point would be so far up, it'd be past the moon, right? But could I choose 2 million or -2 million? And that would even be further away, right? That means that it's always decreasing, even all the way to negative infinity. Because I am always falling until you get to what value? What x value is there?
Oh, 1, 2.
2.
Oh, yeah.
I'm not going to be at 2 because at 2 it's not decreasing, it's not increasing either. Does everybody see that on the interval from negative infinity all the way to 2, so this x-axis right here, all the way far back there to here, the graph itself is decreasing. So on the flip side, where is it increasing? Where's the first number where it starts to take the turn upward? X values, guys. We're talking about x values, not y values. We're not looking for an actual value. At 2, starts to go back up, and it goes on for ever. So it has to be in positive infinity. It will continuously increase from there on out. Can you guys see that? I want you guys to try part B on your own before we come back together. Name any increasing, decreasing, and constant intervals. Does this graph decrease?
Yes.
Where?
And, I don't know what that was. Way far left, right?
Way far left? Like over here?
No, like that line. Would that be decreasing?
This is not decreasing. I think it increases right here. I think everybody can agree with that. But what happens as soon as it hits here? It constant. It plateaus. It's a constant. So, no decrease. I'm not even going to talk about it, but I will say increase. Where is it coming from? The x values? Negative infinity all the way up to the what point? Negative 3. It does say to the nearest 0.5 unit, so just stick with negative 3. Make it easier. If I had to be exact, yes, it is happening at negative 3.1 because that's where the interval change is, right? Okay. And then constant. It's a positive infinity. Not too bad. Think you guys can handle that?
Is that it?
No, that's not it.
Oh.
That's only 2 of 11 slides. Okay. Next. We got some definitions here. Stop your complaining. We could open the windows and turn the heat on again. Okay.
You do that. I'll start a fire.
Okay. Critical points. Guys, I am expanding the critical points a little bit bigger than maybe what the book says. And I say the critical points are those important graphing points. Those graphing, important graphing points. Yeah, I'm going to call them important graphing points. Points of interest. When you make your graphs, what are some points of interest to you? The vertex would be one of them. What's another one? Y-intercept. X-intercept. Origin, sometimes. It's nice to have a placement of where things are relative to the others. Symmetry could be, but not every graph has those. But that would definitely be wouldn't be necessarily a point. It'd be critical information. X-intercepts, Y-intercepts, vertices. What about a max or a min? So max and min also, I would say, critical points. If I was able to graph x-intercepts, y-intercepts, maximum points, minimum points, I could probably make a pretty good representation of a graph based off of those things, right? Whether it be a quadratic, a cubic, a quartact, whatever it happens to be. And so we could definitely make some nice things happen there. Your book then calls some of this stuff extrema. The extrema, guys, is what your book calls where the change happens. So maybe changing points. The changing points, as in where does it go from increasing to decreasing? And those extrema points end up forming the two below it, which is a maximum and minimum. Maximum, what we would call the highest point, and minimum would be the lowest point. Now, I would even say that there are two types of maximums and minimums. You have a max, a true max, they call it absolute max. We're going to do that in the next slide or so. We also have one that's called something else. Now, the book calls it the relative max and min. I think of, if you are from in town, you would be called a, starts with an L, local. So you're local from around here. And so if I'm in the middle, if I'm in the mix of things, I'm a local max or a local min, which means I'm on the inside of the graph. Graphs, guys, sometimes look like this. This point right here is not a maximum because this graph goes on forever in the y direction going up. Therefore, it cannot be the biggest value. But within the confines of the problem, it's called a relative max, local max. Same as the other point on the bottom, local min. Kind of makes sense? Now, a point of inflection. This is like, the book kind of is interesting on this one. They say it's a shape change where increasing or decreasing graphs don't change. So you don't change from increasing to decreasing. It still increases, but it's like a shape change. It's like a hesitation, I call it. Everybody take out their graphing calculator and graph y equals x cubed. I'll give you guys some time for that. So, for those who do not have their stuff with them today, I think we see something that looks or resembles that. Okay. Guys, if you look at this, you zoom in as much as you would like, you should notice that the graph never ever flattens completely out or dips back down. It never changes from an increasing to a decreasing. It's almost like someone took a parabola, kinked it in the middle, and pulled the other end up. So all of a sudden you go directly from decreasing below here to still increasing in a nice even flowing manner. It's still always increasing. Now, I could make a negative x cubed and it could flow the other way. And that would always be decreasing. So the graph is still continuously increasing or continuously increasing, decreasing, whatever. This does not have to happen at the x-axis. It can happen out floating around in space. It doesn't matter. A lot of times you're going to see this is when there's multiple zeros at the same spot. This means that 0 is a solution to the system, right? To the equation. That's a 0. But it just happens to be 3 times. Another way I like to think of this as you have a hesitation. So as you're running up here, you hesitate just a little bit and then keep going. That's a point of inflection. The point of inflection is right in the middle. Another big page of information. Again, it's on the outline. It's in the book. Don't copy it all down. listen to it, is the fact that we already talked about relative and absolute extrema. Relative happens inside. These are relative maximums. Wait a minute, the relative maximums, and this one here we call the absolute max because it's the highest point in the whole entire graph. This point would be a relative minimum. It can't be the minimum because these graphs on both ends go down forever. And remember, one half of the graph can go up, the other half of the graph can go down, so therefore you never have a true max or a true min. All that on the side and the left explains exactly that. So it's fairly easy to follow. You should all understand relative max, relative mins. Local max, local mins. Okay? So let's put that to use. In part A, can you estimate the local max and local mins, minimums, and maximums? Do we have a relative max?
I would say the top one.
This one?
No, the other one. The other one.
That would not be a relative. Actually, this would be the absolute max
Okay.
because that is the highest point on the graph. So if again, estimating, it looks like how far back do I go? This is 0, so 1, negative 1.5, comma, 2. Can everybody? Now we can state the max. Where's the max? 1, 3. Whoops, not 3, 1, 1, 3. And minimum? Is it a minimum or a relative minimum? Relative minimum at what point? Negative 0.5, negative 0.5. Do I have to state any minimum? No, because there is none. Now, look above. It says support your answers using the table. And so how can I use a table to support this? Let's use the example of the maximum point. If I made a table, how can I use a table to demonstrate that 1, 3 is a relative max, aka also the true max? What can you guarantee about 3? It'll be the highest y value. So could I put that in the middle of my t-chart and choose something around it? And if I choose 0 and 2, those numbers will be smaller. Therefore, it has to show that 1, 3, or support it at least. It's not going to guarantee that 1, 3, because we're looking at this, has to be the max. But it at least allows us to say, or support the fact that, yes, 1, 3 is bigger than the others, so therefore it's more likely to be the answer. So if I put 0 in, I get something like 0.
Yep.
If you put in 2, you end up with something like negative 4. What? Sorry, wrong one. No, that's the right one.
You can never report.
Yeah, that'd be about negative 4, right? So, could you say that 3 is the biggest number? Yeah, you're kind of throwing some support behind the fact that you're calling 1, 3 the max. Without having to do 2b, how many relative max, or relative max in this case, are there? How many maxes, relative maxes do we have?
1?
I have a relative max here.
No.
Yeah, this is a relative max.
Okay.
And then, whoop, right there. Wait a minute, I had to duck down a little bit right here. That means this must be a relative min, but guess what? This one is right here. a relative min. There are no max or mins, absolutely, here. Because the graph goes up forever, and the graph goes down forever. So there's no max and min, there's only relative max and mins. Questions? Cool stuff? Now, going to this, why we need our calculators is because you need calculus to confirm increasing, decreasing, and relative max and absolute maxes. We take derivatives, guys. We find out where slopes are. And when the slope is 0, that's where it's going to top out or bottom out. We're not there yet, so guess what? Make our calculator do the work for us. So here we go. Using a graphing calculator, I want you to approximate to the nearest 100th the x value where a max or a min occurs. So take your calculator, graph 7 minus 5x minus 6x squared. So as you're doing that, hopefully you recognize that, hey, that's out of order. Your calculator doesn't care. Number 2, hey, that is a what? What kind of function is that? It's a quadratic. It's a parabola. That opens which way? Down. Therefore, it should have a maximum. So, as you're typing that equation in, your results should look something like so.
This one does care if you type it in. It has to be exact.
You have to be the exact, as in you need to be the same. But if you could put that in standard form, you'll get the same graph. That's what I was trying to hint at. Your calculator will put values in for x no matter which way you put it, as long as it's still the same equation. So what we need to do is make our calculators do the work for us. Here's the cool thing. We've already been doing is making the calculator find the values for us. You now can go to second, calculate. And again, you have options of like 7 or 8 things. You can see that from the graph, there was a maximum. So guess what? Click 4, which is the maximum button. And what you're going to recognize, guys, is that there's a small blinking little star. Hit second, calculate. Second trace.
0%.
Second, calc. You hit it once already. What's going on? Take your star, that blinking light, and notice the directions. On your calculator it says left bound. Need to go to the point where your graph, you see the star, hit your arrows to the left, 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 left. Make the arrow sit someplace right there, that little star, hit enter. Anywhere on the left side of the hump. And then it pops up the question, right bound. Now, your blinking cursor is still here. Page it to the right. On the other side, it doesn't matter as long as it's on the other side of that hump. Hit enter.
It says guess.
Oh, it wants you to make a guess. Who cares? Don't make a guess. Hit enter again. And you find out you can get the x value to the hundredths. Negative 0.42. Guys, your homework is on the board. I'm going to finish the video. Watch the rest of the video. It's not much left. The next question is g of x is 2x cubed minus 4x squared minus x plus 5. So again, I'm not going to do the full thing here, but if we put this on our graphing calculators, we would see that it's a general N-style shape, and we should recognize that we will have a local max and a local min. And so this is the local max, the local min, and again, go to your calculator, make sure that you hit second, or type in the equation, hit second calculate, and when you hit second calculate and hit maximum, make sure that you put your little star for the left bound and the right bounds just to the right and left of that maximum, and then again of the minimum. So therefore you find the maximum we want, because your calculator is only going to find the maximum value that is within your interval you choose. So if by chance you chose your interval to be here to here, it's going to take that y value as your maximum because that is the tallest value or biggest value in that interval. So if I limit it to just where it peaks, it will find the maximum and do the same thing this time for a minimum for here. And I'll let you guys figure that out. Your homework for day 1 is chapter 1.4, page 40, 1 through 31 every 3. We'll finish up 1.4 tomorrow, and then we'll have a review and then a quiz. Looks like it'll be on Friday. Have a great day.